everyone. So I wanted to get back to our vector addition kernel here and take kind of the next steps in the end-to-end process. And very first thing we need to do after completing our kernel is verify its numerical fidelity. So we want to verify numerical fidelity. And to do that, I just want to introduce an API called torch.allclose, which I use quite extensively. It's a little bit different than how the tutorial checked their results. But regardless, to write out our validity test here, first thing we want to do, just for reproducibility, we will seed, there we go, manual seed, whatever. So this will actually seed both CPU and GPU, so that will cover pretty comprehensively. We need to make a vector size just for a generic test. I'm just going to go with 8192, just to have a reasonable size vector. This is kind of along the lines of a lot of LLM type sizes. So that gives us our initial vector. Next thing, we need our A and our B samples. So we'll do torch.rand, vector size, and key thing is we want to make sure it's on the GPU. Oops. So here and B can just be torch.rand like. So this will clone it, but it will not actually keep, it'll resubmit for the random data aspect, but the rest of it, size and device will be preserved, so we don't have to bother rewriting all that out. So that gives us our A and our B. And I guess what we want to do now is just compare it to PyTorch. So let's call it torch res equals A plus B. So that gives us our sort of master answer, so to speak. And let's compare it to our kernel that we wrote. So Triton res equals vector addition, A, B. And then what we want to do here is once we have that, we want to do a comparison between the two results sets, make sure they're identical. So this is what I was talking about, torch.allclose. And what are we comparing? Torch result with Triton result. Here, and I just want to highlight, you have A to L, and which is absolute tolerance, and R to L, relative tolerance. You will have to start adjusting these over time, particularly when you get into things like different matrix multiplication and so forth, where just by virtue of chunking, you're going to have more rounding, and so therefore you need to account for the fact that the rounding from the chunking will actually have a slight variance, and you need to account for that. So anyway, torch res, Triton res. And actually, let's preserve our result. Fidelity correct equals torch.allclose. And let's just print result of fidelity. Right here. Oops. Fidelity correct equals. And that should do it. So that gives us a little function here. Let's just set up if a little master controller for what we're going to do here, because we want to do benchmarking next, assuming that we get the fidelity correct. If name equals magic underscore main, that's right. It doesn't like, missing here. So we got our dunders and equal. And, oh, we didn't put this in a function. Oops. To add that. So let's define verify numerics and returnable. So let's tab this through, save it. Okay, that looks good. Because what we want to do is we want to have the ability to toggle between whether we want to verify numerics or we want to run benchmarking, which we'll do the next step. And I'll just make that a separate video to keep that modularized as well. But anyway, if name equals main, we're going to run verify numerics, no parameters. I think that does it. So let's go ahead and run it. Our kernel, make sure we're calling our kernel, yep, vector addition, okay. So let's fire this off. And we got an error in our kernel. Traceback numerics, vec size. Move myself out of the way here. And easy error, device is not GPU, it's CUDA. So anyway, let's fire this off. Okay, and getting to an error in our kernel, assert a.is CUDA. This is a method, not a function call. Okay, so we'll try again. and fidelity correct equals true. So what we verified is that our Triton kernel does exactly the same numerical accuracy or fidelity as PyTorch itself. So we're off to a great start there. I think let's do benchmarking and a little bit of tuning in the next video to kind of wrap up the whole end-to-end process of writing our own vector addition kernel. So see you in the next video.